Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here is the essay, with a focus on the critical evaluation of Srinivasa Ramanujan's collected papers. Adhering to all given constraints, the legacy of Srinivasa Ramanujan stands as a testament to the power of mathematical intuition, a beacon illuminating the landscape of number theory and analysis. His contributions, though tragically cut short by an early death, continue to resonate within the mathematical community, inspiring awe and demanding rigorous scrutiny. This essay embarks on a journey through the 19 collected papers, a foundational anthology of his initial forays into the world of mathematical discovery. We will evaluate the claims, arguments, and methodologies presented within these early works, offering a critical appraisal of their significance and enduring impact. Section 1: Modular Equations and Approximations to Pi. Ramanujan's investigations into modular equations constitute a significant portion of his early research, revealing a profound understanding of elliptic functions and their intricate relationships. One characteristic exploration involves the derivation of highly accurate approximations to pi. He presented a number of these formulae, often without rigorous proof in the conventional sense, relying instead upon intuition and pattern recognition. One such approximation, presented within this section, states that pi is approximately equal to 355 divided by 113, a result known to offer remarkable accuracy. This claim demonstrates a deep familiarity with the properties of elliptic integrals and modular functions. The evaluation of such claims necessitates a careful reconstruction of the underlying logic, often absent in Ramanujan's original presentations. Later mathematicians, notably Bruce Berndt, have dedicated themselves to providing formal justifications for these results, employing sophisticated techniques from complex analysis and number theory. The effectiveness of these approximations rests upon the rapid convergence of certain infinite series, a phenomenon linked to the modular invariance of the elliptic function involved. The true genius revealed itself in the uncanny ability to identify these relationships and express them in closed form. The validity in this section then is not in the formal proofs given at the time are the accurate end result of these Section 2: Highly Composite Numbers. This section delves into the fascinating realm of highly composite numbers, integers possessing a greater number of divisors than any integer below them. Ramanujan offers a detailed analysis of the properties of such numbers, striving to characterize their structure and distribution. One key claim made is regarding the asymptotic behavior of the number of highly composite numbers less than a given value. He presents conjectures, later partially confirmed by Paul Erdős, concerning the growth rate of this function. Evaluation of this section necessitates appreciating the delicate interplay between prime number theory and multiplicative number theory. The claim is not an explicit formula, but rather an approximation asserting that the number of highly composite numbers grows slower than any power of the natural logarithm. The method employed involves an iterative process of refining the prime factorization of highly composite numbers. He recognized that they must be composed of small prime factors raised to relatively large powers. The accuracy of this analysis rests upon the precise understanding of these exponents and their relationship to the overall size of the number. The asymptotic claims, while lacking formal proof at the time, represent profound insight into the distribution of these special Section 3: Some properties of Pn. The number of partitions of n. Ramanujan's work on the partition function, denoted Pn, stands as one of his most influential contributions to number theory. In collaboration with G. H. Hardy, he derived an asymptotic formula for Pn that revolutionized the study of partitions. The analysis in this section, focusing on the properties of Pn, claims a radical improvement in computational efficiency within the theoretical framework used at the time. This allows number theorists to make claims regarding the total number of partitions of very large numbers previously thought impossible to calculate. The derivation is a formidable undertaking, combining techniques from analytic number theory, modular forms, and the theory of elliptic functions. The validity of this formula hinges upon the modular invariance of the generating function for Pn, a fact deeply rooted in the theory of modular forms. This section illustrates the power of analytic methods at attacking problems in combinatorics and provides a testament to the fruitful collaboration between Ramanujan and Hardy. The true significance lies in its practical implications, enabling mathematicians to approximate the value of P's n with remarkable accuracy for large values of n. Section 4 Proof of some formulae enunciated by Mr. Ramanujan in question 292 of Journal of the Indian Mathematical Society. This section contains proofs of multiple formulae, originally presented as unproven conjectures in the Journal of the Indian Mathematical Society. These formulas often involve intricate identities relating infinite series, definite integrals, and special functions. Evaluation of these proofs requires a careful verification of the algebraic manipulations and the application of appropriate convergence theorems. One notable result presented in this section pertains to the evaluation of a certain definite integral involving trigonometric functions. The proof demonstrates a clever application of integration by parts and the residue theorem. The beauty of this result lies in its apparent simplicity, disguising the underlying sophistication of the analysis. The claim is that by following these very specific steps, a simplification can be performed, leading to a closed-form expression for the integral, a claim that stands up to scrutiny through replication. Section 5 Irregular numbers. Ramanujan delves into the properties of irregular numbers, those integers which are not the sum of any two primes. This section involves a consideration of the distribution and characteristics of irregular numbers. The central claim involves providing an estimate of the number of irregular numbers up to a certain limit. The analysis involves a combination of sieving techniques and heuristic arguments. Evaluation of this section demands acknowledging the inherent difficulty in proving results about the distribution of primes. The claim relies on the Goldbar conjecture, which posits that every even integer greater than 2 can be expressed as the sum of two primes, although this section does not explicitly state that it is relying on this conjecture. The absence of a rigorous proof of this conjecture introduces a degree of uncertainty into the analysis. Nevertheless, the asymptotic estimate provided offers valuable insight into the distribution of irregular numbers and offers a novel perspective on prime number theory. Section 6 New expressions for Riemann's functions zetas and et. Here, Ramanujan explores novel expressions for the Riemann zeta function, zetas, and its associated entire function, E of t, seeking to shed light on their properties and behavior. This section focuses on finding new series representations of these functions, allowing them to be analyzed and calculated more easily. The central claim is the derivation of convergent series representations for these functions that are valid over a wider range of complex values. The analysis employs a combination of contour integration, functional equations, and special function identities. Evaluation of this section requires understanding the central role of the Riemann zeta function in number theory. The convergence of the derived series hinges upon the analytic properties of the gamma function and the judicious choice of integration contours. The significance of these new expressions lies in their potential to facilitate the computation of zetas and et and to provide new insights into their zeros, particularly those lying on the critical line, an argument that hinges upon the analytic continuation of previously known functions. Section 7 Some definite integrals. Continuing his exploration of integral calculus, Ramanujan presents a collection of definite integrals, Often exhibiting remarkable symmetry and elegance, this section showcases his mastery of integration techniques and his ability to discover surprising relationships between seemingly unrelated functions. The central claim is the evaluation of these integrals in closed form, often involving special functions such as the gamma function and the hypergeometric function. The analysis employs a combination of contour integration, differentiation under the integral sign, and the application of known integral identities. Evaluation of this section requires a meticulous verification of the integral evaluations, often involving intricate algebraic manipulations. The beauty of these results lies in their aesthetic appeal and in their potential to be applied to other areas of mathematics and physics. This section shows his ability to apply these complex techniques to integrals that are useful for solving other problems in mathematics. Section 8 on the integral 0e x2a2 x2 dx and allied integrals. Ramanujan meticulously investigates the integral from 0 to infinity of the exponential of the negative quantity, the sum of x squared and a squared over x squared with respect to x, along with related integrals. The claim made within is the derivation of closed-form expressions for these integrals involving Bessel functions and modified Bessel functions. The analysis makes heavy use of contour integration in the complex plane and meticulous manipulation of the integral. To rigorously evaluate this claim, one must confirm the validity of the contour integration steps, ensuring that the contributions from the contours at infinity vanish appropriately. The connection between this integral and Bessel functions is significant, highlighting the interplay between seemingly disparate areas of mathematics. These results find applications in diverse fields, including physics and engineering, illustrating the practical relevance of Ramanujan's Section 9 on certain trigonometric sums and their applications in the theory of This section focuses on the study of trigonometric sums and their applications to problems in number theory. Ramanujan examines the behavior of such sums, seeking to derive asymptotic formulas and to establish connections with other number-theoretic objects. The analysis involves a combination of analytic techniques, such as the saddle point method, and number-theoretic arguments, such as the theory of quadratic recursion. Evaluation of this section requires appreciating the importance of trigonometric sums in number theory, particularly in the study of the distribution of primes. The claim is an improved understanding of the convergence behavior of these sums. The applications of these results to problems such as the estimation of the number of lattice points in a circle demonstrate the versatility of Ramanujan's techniques. Section 10. Congruence properties of partition function. This section continues the exploration of the partition function, Pn, building upon the earlier work with G. H. Hardy. Here, Ramanujan focuses on uncovering congruence properties of Pn, observing that it exhibits remarkable patterns when considered modulo certain integers. The central claim is the discovery of several key congruences, such as the fact that P of 5 times n plus 4 is divisible by 5, P of 7 times n plus 5 is divisible by 7, and P of 11 times n plus 6 is divisible by 11. The analysis employs a combination of modular forms, generating functions, and algebraic manipulations. Evaluation of this section necessitates a deep understanding of modular arithmetic and the theory of modular forms. These congruences reveal a hidden structure within the partition function, suggesting connections to other areas of mathematics. The claim concerning divisibility by 5, 7, and 11 is verified through meticulous calculation and application of identities involving modular forms. These results represent a significant advance in the understanding of the partition function and its arithmetic properties. Section 11. Algebraic relations between certain infinite products. Ramanujan investigates algebraic relationships between certain infinite products, uncovering surprising identities that connect seemingly disparate mathematical objects. This section focuses on finding relationships between different types of infinite products, often involving theta functions and other special functions. The central claim is the discovery of numerous novel identities relating these products. The analysis employs a combination of algebraic manipulation, functional equations, and the theory of elliptic function. Evaluation of this section requires a keen eye for pattern recognition and a willingness to engage with complex algebraic expressions. The beauty of these identities lies in their unexpectedness and in their potential to be applied to other areas of mathematics and physics. The claim that these identities exist requires careful checking of the algebraic manipulations that lead to them. Section 12 on product 1 xn. Ramanujan analyzes the infinite product from n equals 1 to infinity of 1 plus x to the power of n. This section seeks to understand the convergence properties of this product and its relationship to other mathematical objects. The central claim involves deriving an asymptotic formula for the product as x approaches 1. The analysis employs a combination of analytic techniques and number-theoretic arguments. Evaluation of this section involves a careful consideration of the convergence conditions and the validity of the asymptotic approximations. The results in this section shed light on the behavior of infinite products and their connections to other areas of mathematics. This analysis gives a better understanding of how to deal with these infinite products and their properties. Section 13. Some formulae in the analytic theory of numbers. Ramanujan presents a collection of formulas related to the analytic theory of numbers, showcasing his mastery of analytic techniques and his ability to discover deep connections between seemingly unrelated mathematical objects. This section contains various formulas relating to prime numbers, the zeta function, and other number-theoretic objects. The central claim is the development of novel tools for analyzing these objects. The analysis employs a combination of analytic techniques, contour integration, and functional equations. Evaluation of this section requires a broad knowledge of analytic number theory and a willingness to engage with complex mathematical arguments. The formulas presented in this section have the potential to be applied to a wide range of problems in number theory, offering new insights into the distribution of primes and the properties of the zeta function. The claim is that these formulae are useful tools for people working in analytic number theory. Section 14 on the expression of numbers in the form x2 by 2. Ramanujan investigates the problem of representing integers in the form ix squared plus by squared, where I and b are given integers. This section seeks to determine which integers can be expressed in this form and count the number of such representations. The central claim involves deriving formulas for the number of representations in terms of modular forms and other special functions. The analysis employs a combination of number-theoretic arguments and the theory of modular forms. Evaluation of this section requires a deep understanding of quadratic forms and the theory of modular forms. The results in this section are closely related to the class number problem and have implications for the study of elliptic curves. The claim that these numbers are represented in this very specific form relies heavily on the results from his work in modular forms. Section 15 on certain arithmetical functions. Ramanujan explores the properties of various arithmetical functions, such as the divisor function and the Euler-Totient function. This section seeks to establish relationships between these functions and to derive asymptotic formulas for their behavior. The central claim involves uncovering hidden connections between different arithmetical functions. The analysis employs a combination of number-theoretic arguments, analytic techniques, and the theory of modular forms. Evaluation of this section requires a broad knowledge of number theory and a willingness to engage with complex mathematical arguments. The results in this section have implications for the study of the distribution of prime numbers and the properties of multiplicative functions. This section is focused on taking the known details of these arithmetical functions and using them in novel. In conclusion, Srinivasa Ramanujan's collected papers represent a treasure trove of mathematical insights, offering a glimpse into the mind of a true genius. While some of the claims presented lacked rigorous proofs at the time of their publication, subsequent work by other mathematicians has largely confirmed their validity and significance. The enduring impact of these papers lies not only in their specific results but also in their influence on the development of number theory and analysis. They continue to inspire mathematicians today, serving as a reminder of the power of intuition and the beauty of mathematical discovery. His work serves as a reminder that even without formal training, exceptional results can be achieved. The legacy of Ramanujan stands as a testament to the enduring power of the human mind to unlock the secrets of the universe, expressed in the elegant language of mathematics.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.